So I want to talk about this paper that just appeared on Archive, October 2024. I'll leave a link in the description by Mehmet Çelik et al. Mehmet is from the University of Texas A&M, called Exploring a Geometric Conjecture. And as the abstract says, this has to do with YouTube video that I made in 2021. Let me get to the phenomenon here so we can discuss it, and I hopefully will introduce a new extension of it. Okay. So the phenomenon in that 2021 video has to do with a Poncelet family of triangles inscribed in a circle and circumscribing a concentric ellipse. Okay? So nothing too exotic here. You can see here that over the family, both the perimeter and the area are varying. Now, on that video, I brought in a very classical concept of a power circle of a triangle. A triangle has 3 power circles, and let's just look at the first one here to start, right? So a power circle, or the first power circle of this triangle, has its center at the midpoint of some edge, for example, P1, P2, so here's the midpoint, this red dot, and it passes through the opposing vertex P3. So as I animate Poncelet, I can watch this power circle, this first power circle, and I'm showing here that its area is variable. However, if I repeat this construction for the remainder 2 power circles, I show in that 2021 video that the sum of their areas shown up here is invariable. So this was kind of interesting. And then some 2021 to 2024. Okay, so we're talking about 3 years later. I'm very happy to see that there's a proof based on sophisticated tools called Blaschke products. Okay, so I want to talk about an interesting further phenomenon here. Let's erase the power circles. Now let's consider the same family, but with 5 edges, like that. So this is a Poncelet family, okay, of pentagons inscribed in a circle and circumscribing a concentric ellipse. Very well. Let's go ahead and draw its first, now with a twist, power circle. I can still find a midpoint of a particular edge, for example, this red dot, and then locate, let's call this the opposing vertex to that edge. Since n is odd, what I mean by opposing vertex is unambiguous. And I can just draw this circle, and I can watch that circle just like I did for triangles. And again, the area of this first power circle, as you see here, is variable. Now let's go ahead and draw all 5 power circles and look at what happens to the sum of their areas. And they too are invariable. Now does this hold for n equals 7? It does. So here's a family of heptagons. You can see that the area of the 7 power circles of this family is conserved. And how about 9 also holds? So here's the sum of the area. Let's make this be more, yes, let's make this be as eccentric as possible. Let's show what I'm talking about here. So, you know, as you get to larger n's, the variability of each individual area, you know, is further down in the decimals here of this number. Okay, but lo and behold, it looks like it is the case that if I draw all power circles, their sum is still constant, irrespective of odd n. Now, in the 2021 video, I also talk about, let's go back to 3, right? I also talk about another Poncelet family that has this property, and that is the homothetic family. So what is a homothetic family? To review it again, it's a family whose which is a homothetic image of the 2 concentric circles. So put 2 concentric circles like that, with the outer one having twice the radius of the inner one, you get a family of rotating equilaterals. And then if I apply an affinity to it, I get this homothetic family. Because of the affinity, it preserves the area, which is not the case in the previous family. And I can draw one of its power circles. And notice that its area is variable. But if I draw the 3, I get a constant sum of power circle areas. Does this hold for n equals 5? Looks like it does. You can see here that the sum of the 5 power circles for the homothetic family is conserved. And for 7, also conserved. And for 9, conserved here up to 8 decimal places, right? But let's call this a conjecture. So let's go back to 5, for example. And I want to show you another family, which I did not cover in the 2021 video, but which also preserves that. And that is the the MacBeath family. What is a MacBeath family? Let's review it. The MacBeath family, let's start with n equals 3, because it's easier to explain, is a family of triangles inscribed in a circle and circumscribing its fixed MacBeath in ellipse. What is a MacBeath in ellipse? It has a focus at the center of the outer of the fixed circumcircle. So x3, and then the other focus, its orthogonal image, is the orthocenter, which is also fixed in this family, but this is not germane. What's germane is I can also draw one power circle for this family. Here's the midpoint of side P1, P2, and here's the circle passing through the opposite vertex. I can watch that its area is variable, but that the sum of the areas is conserved for the MacBeath. How about MacBeath n equals 5? I also got the conservation. Let's just look at it more carefully here. Just one power circle. I have one power circle. This is, let's get it more eccentric here. So I still have this generalized MacBeath in ellipse now for n equals 5. One power circle, variable area, but the sum of the 5 is invariable. 31.01 here. And how about n equals 7? We got invariability as well, and n equals 9, invariability as well. Okay, guys, so that's all I have. I'm very proud that a group of researchers took on the task of proving this interesting property, and I just want to thank them for having written this beautiful paper. I'll leave a link in the description. And I'm just proposing this new set of conjectures, right? So see you in the next video. Thank you very much.